this video.
Hello, in this session we will discuss Lechateliers principle. We will try to understand the principle, Lechateliers principle, through equilibrium constants and their quantitative dependence on pressure, temperature and concentration. We will give more emphasis to the relation between equilibrium constant and its relation with temperature, pressure and concentration. Through this we will try to understand the Lechateliers principle. So first we will go with the definition. What is Lechateliers principle? According to Lechateliers principle, when an equilibrium is subjected to any change or perturbed, the equilibrium will always be displaced in such a way to oppose the applied change. That is, equilibrium is shifted in a direction that reduces the change caused by an independent variable. What is independent variable? Independent variable is maybe temperature, pressure, inert gas or concentration. We will discuss these four independent variables. Again I am repeating, we will discuss temperature, pressure, inert gas, addition of inert gas and concentration, initial concentration of the reactants. So these are the four independent variables we will discuss during this session. So why that happens? What is the reason behind that? That the chemical system or the chemical equilibrium does not want to be get disturbed, because at equilibrium the Gibbs energy is already at a state of minimum. We have studied that the change in Gibbs energy is zero at equilibrium, means the Gibbs energy is at its minimum value at the state of equilibrium, and the system does not want to lose its state of comfort. Every system wants to attain the least Gibbs energy. So at equilibrium the system is already at the state of least energy position, so it does not want to lose its comfort. When it is disturbed from that equilibrium position, it tries to regain that equilibrium position by doing some auto rearrangement or auto twinning kind of effect. So as I said, we will discuss four independent variables starting from the effect of temperature on equilibrium constant. As I have also said, we will try to understand through a more quantitative approach. So before going to study the effect of temperature and equilibrium constant, let's understand the Van 't Hoff equation. We have studied in the last lectures. The Van 't Hoff equation is d ln k over dt is equal to delta R H0 by RT square. Delta R H0 is the reaction enthalpy at standard state and k is the equilibrium constant, T is temperature, R is the gas constant. The integrated form of this equation, this Van 't Hoff equation, is ln k2 by k1 is equal to delta R is 0 by R T2 minus T1 divided by T1 into T2. T1 and T2 are two temperatures at two different states, initial state and final state. Similarly, K1 and K2 are equilibrium constants at two different states. And this integrated equation is applicable when the reaction enthalpy at standard state is independent of temperature. We'll assume that the reaction enthalpy at standard state is independent of temperature, so this integrated equation is applicable. So we will use these two equations, these two Van 't Hoff equations, to understand the effect of temperature on equilibrium constant. Now first let's understand the first case. Suppose there is a endothermic reaction. Endothermic reaction means this delta R H0 is positive. The enthalpy change in enthalpy for endothermic reaction is positive, so delta R H0 is positive. So if we increase the reaction, if we increase the temperature for endothermic reaction, means this delta R H0 is positive and I am increasing the temperature, means T2 is more, so this whole RHS will be what? This RHS will be positive, so my K2 will be more, So I can say for endothermic reaction, when I increase the temperature, equilibrium constant also increases. Again I am saying, for endothermic reaction, when I increase the temperature, the equilibrium constant will also increase. What does that mean? Equilibrium constant increases. That means my reaction is going towards product formation, or my reaction is going towards right hand side, or more and more products are forming. Now let's consider the second case. What is the second case? For exothermic reaction. For exothermic reaction, the reaction enthalpy is negative. So this numerator is negative. So if I increase the temperature for exothermic reaction, this T2 will be more. So this total RHS term is going to be more and more negative. So if this RHS term is going to be negative, what will happen? My equilibrium constant will decrease. My final equilibrium constant will decrease because the RHS is going to be negative, because the reaction enthalpy for exothermic reaction is negative. So I can say for exothermic reaction, when I increase my temperature, my equilibrium constant is going to decrease. What does that mean? That means the reaction will go towards reactant side, means the reaction will go in a backward direction, or more and more reactants will form. The reaction will not proceed towards product formation. Again I am repeating, for exothermic reaction, as the temperature is increased, the equilibrium constant decreases and more reactants are formed. The reaction proceeds in a backward direction. Okay. So this is the effect of temperature on equilibrium constant. Now let's consider the effect of pressure. So before going to understand the effect of pressure, we have studied the relation between equilibrium constant in terms of mole fraction and equilibrium constant in terms of pressure. So the relation is equilibrium constant in terms of mole fraction is given as equilibrium constant in terms of pressure into P over P0. P is the pressure of the gas. Okay, total pressure of the system, equilibrium system, total pressure of equilibrium system. P0 is any reference pressure, standard state pressure I can say. At equilibrium state is raised to the power minus V. What is V? V is difference of gaseous products minus gaseous reactants. Again I am repeating, V is sum of gaseous products minus sum of gaseous reactants. Okay, so this is the relation. We will use this relation to understand the effect of pressure on equilibrium constant. So first case, when amount of gaseous products is equal to same as amount of gaseous reactants, then what will happen to V? V will be, as I said, V is sum of stoichiometric coefficients of gaseous products minus sum of stoichiometric coefficients of gaseous reactants. So I am saying the amount of gaseous product is equal to a gaseous reactant. So this sum of stoichiometric coefficients of gaseous product will be same as sum of stoichiometric coefficients of gaseous reactant. So essentially V will be 0. So if V is 0, what will happen? Kx and Kp, they will be same. What is Kx? Kx is equilibrium constant in terms of mole fraction of the gas system, or what is Kp? Equilibrium constant in terms of partial pressure of the gases. Okay, therefore change in gas pressure. So if I change the gas pressure, either if I increase the gas pressure or decrease the gas pressure, does not affect the equilibrium mole fraction of reactants and products. That is, equilibrium is not disturbed. So if the number of gaseous products, number of moles of gaseous products is equal to number of moles of gaseous reactants, and under such condition, if I change the pressure, then the equilibrium will not be disturbed. This is the first case. Second case, under effect of pressure, when the number of moles of gaseous products is more than number of moles of gaseous reactant. If that is the case, V will be positive, because the number of moles of gaseous reactant is more, gaseous product is more and reactant is less. So V is V, what is the definition of V? V is sum of number of moles of products, gaseous products, minus sum of number of moles of gaseous reactant. So under case 2, V will be positive. So if V is positive, what will happen to Kx? if V is positive, if when pressure, total pressure increases, if this pressure is increasing and it is a there is a negative power, okay, V is positive means the total the actual power will be negative. So if I increase the pressure, the Kx will decrease. So if I increase the pressure, the Kx the equilibrium constant will decrease. That is, mole fraction of reactants, equilibrium constant in terms of mole fraction decreases, Kx is decreasing. So what does that mean? Mole fraction of reactants will be greater than mole fraction of products, means equilibrium is shifted backwards or backward reaction takes place. Again I am repeating the whole case. When the amount of gaseous product is greater than gaseous reactants, and under such condition, when the amount of number of moles of gaseous product is more than gaseous reactant, and under such condition, if I increase my pressure, total pressure, the Kx will decrease. What is Kx? Kx is equilibrium constant in terms of mole fraction. So Kx decreases means what? The mole fraction of reactant is more than mole fraction of products, because Kx is mole fraction of products divided by mole fraction of reactants, each raised to their powers. We have studied in detail about Kx in previous sessions, so I will not go to that details. Kx decreases means mole fraction of reactants will be more than mole fraction of products. And what does that further mean? That means equilibrium is shifted backward, means backward reaction takes place, means more and more reactants are forming. Okay, more and more reactant products are again forming more and more reactants. Okay, so that is the case 2. Now case 3, when the amount of gaseous products is less than the number of moles of gaseous reactant. Again I am saying, if the number of moles of gaseous reactants is more than number of moles of gaseous product, under that condition V will be negative. If V is negative, suppose V is negative here, and the both negative and negative will be positive. So if I increase my pressure, Kx will also increase. So when V is negative, when the number of moles of gaseous products is less than number of moles of gaseous reactants, okay, then V will be negative. So my P will, this total, the power term will be positive. So when I increase the pressure, Kx will also increase, means equilibrium constant in terms of mole fraction will increase. What does that mean? Mole fraction of the product will be more than mole fraction of the reactants. And what does that mean in terms of the reaction? That means equilibrium will be shifted in forward direction, or more and more products will be formed. So this is the third case. Now what is the fourth case? If a reaction involves only all the three cases we have discussed involves only gaseous reactants or products. Now suppose there is a reaction which involves solids and liquids. What will be the effect of pressure? For if the reaction involves solids and liquids, then the effect of pressure on equilibrium will be very small. There will be not marginal effect of change of pressure on the equilibrium constant. When the reactants and products are in gaseous form, then only the effect of change of pressure will be felt on the equilibrium constant. If the reactants and products are either in liquid state or solid state, if all the reactants and products are in either in liquid state or solid state, then the change in pressure will not be felt much. Okay, so again I am summarizing the whole thing. So if the number of gaseous reactants and products are same, and if I am increasing the pressure, then there is no change on equilibrium constant. If the number of moles of gaseous product is more than number of moles of gaseous reactant, and if I am increasing the pressure, then the reaction will form more and more reactants. It will go towards backward. And the third case was when the number of moles of gaseous reactants is more than gaseous products, and if I am increasing the pressure of the gas, then the reaction will proceed towards forward direction, means more and more products will form. If I decrease the temperature, then the reverse will happen. whatever condition I have said for increase of pressure, if I decrease the pressure, the opposite thing will happen. So the one more case can be added here for case 2 and case 3. When pressure decreases, the opposite thing will happen. Then we'll discuss the effect of addition of inert gas. This is important. This is important. What happens if I add an inert gas to my equilibrium system? The addition of inert gas at constant temperature and volume. The first case is inert gas is added to the equilibrium system at constant temperature and constant volume. So what will happen? To understand that, let's again write the expression Kp and Kx. We have studied this expression, the relation between Kp and Kx. What is Kp? Equilibrium constant in terms of partial pressure of the components, and what is Kx? Equilibrium constant in terms of mole fraction of the components of the system. So Kp will be P by P0 root over V, square to the power V. Kx, V is again sum of number of moles of gaseous products minus sum of number of moles of gaseous reactant. What is P? P is total pressure. P0 is a reference state pressure. Generally it is the standard state pressure. So the first case we are assuming is inert gas is added at constant temperature and volume. Now if my volume is constant and temperature is constant, so let's try to understand in a more physical way. Gas is there and I am keeping my volume constant and temperature constant. So if I increase, then the pressure can change. The gas pressure can change. The gas pressure may increase or gas pressure. So the pressure is not a constant here. If I add inert gas, the gas pressure will increase. Again I am saying my temperature and volume is constant. To that system, if I am adding inert gas, the total pressure will increase because inert gas will contribute to some additional pressure. So inert gas, so the total pressure of the system will increase. But while calculating the equilibrium constant, we are not bothered about inert gas. We are more bothered about reactants and products. So what is the pressure of reactants and products? The pressure of reactants and products before addition of inert gas will be same as the pressure of reactants and products after addition of inert gas. Again I am repeating, the addition of inert gas will not have any effect on the partial pressures of reactants and products. To say that, I can say that partial pressure of reactant and partial pressure of product before addition of inert gas will be same as partial pressure of reactant plus partial pressure of products after addition of inert gas. Okay, so this total pressure is partial pressure of reactant plus partial pressure of products, because we are not counting the partial pressure of inert gas in our equilibrium system. That does not have any additional input. So our equilibrium is only deals with the partial pressure of reactant and products. If we add inert gas, then well and good, there is no problem. The partial pressure of reactant and product before addition of inert gas and after addition of inert gas remains same. That means the equilibrium constant will also remain same. If P is not changing, so how does the equilibrium constant will change? That will also not change. So if an inert gas is added at constant temperature and volume, the equilibrium constant will not change. Now the second case is the very important case. Addition of inert gas at constant temperature and constant pressure. Here is the important case. Here I am not allowing my pressure to change. Means I am adding inert gas to the system where already reactant and product is there. I am adding to that system, I am adding inert gas and I am not allowing the system to change. So what will happen? Again I will use this the same expression of Kp and Kx, that is equilibrium constant in terms of partial pressure and equilibrium constant in terms of mole fraction. So we will understand through this expression. So before addition of inert gas, what was the total pressure? The total pressure was sum of partial pressure of reactants and products. After addition of inert gas, the total pressure is sum of partial pressure of reactant, product and inert gas. This is after addition of what? inert gas, but I am saying the total pressure will not change. Okay, the total, try to understand, the total pressure is not changing after addition of inert gas. So what will happen? How that can be possible? That means partial pressure before addition of inert gas. So the pressure before addition of inert gas was due to partial pressure of reactant and products. Now pressure after addition of inert gas is due to what? Partial pressure of reactant, product and inert gas. And we are imposing the conditions that pressure is not changing, means both of them are same, means after addition of inert gas, the partial pressure of reactant and product will decrease. Again I am repeating, after addition of inert gas, the partial pressure of reactant and product will decrease. Okay, so but the total pressure remains constant when inert gas is added. This means that the sum of partial pressure of reactant and product will decrease, then only the total pressure will remain same. Therefore final pressure of reactant plus product, final pressure means after addition of inert gas, will be less than initial total pressure of reactant and product. And again as I just mentioned, during calculation of equilibrium constant, we are least bothered about the pressure of the inert gas. That does not contribute to the equilibrium constant. Only two things contribute. Those are partial pressure of reactants and partial pressure of products. Partial pressure of inert gas will not contribute to equilibrium constant. So our important point to note that pressure of reactant and product after addition of inert gas is less than pressure of reactant and product before addition of inert gas. So if partial pressure of inert gas is known, then we can find out the final total pressure can be precise. And if I know the partial pressure of inert gas, then we can use this expression. That's what this statement says. Therefore partial pressure of reactant and product before addition of inert gas will be this is wrongly written here. So partial pressure of reactant and product, okay, before addition of inert gas will be more than, this will be greater than, okay, this will be greater than partial pressure of reactant and product after addition of inert gas. So after addition of inert gas, this P decreases. That's what I want to say. After addition of inert gas, this should be greater than sign. Please correct this. So after addition of inert gas, this pressure decreases. So if pressure decreases, the equilibrium constant will also decrease, means the reaction will go towards reactant side, or it will go towards what? It will go towards backward direction, or more and more reactants will form. So I can say the addition of inert gas at constant temperature and pressure causes the reaction to go in a backward direction. In a backward direction. Then we will discuss the last independent variable, that is effect of initial composition on equilibrium. Effect of initial composition on equilibrium composition for a equilibrium constant. This should be equilibrium constant. Effect of initial composition on equilibrium constant for a reaction. Okay, so we will understand what is the effect of initial composition on equilibrium constant. We will understand this through two reactions. Let the first reaction is nitrogen tetroxide is giving nitrogen dioxide. Okay, nitrogen tetroxide is giving nitrogen dioxide. Suppose the initial number of mole is 1, 0. At equilibrium 1 minus xi, 2 xi. Xi is the extent of reaction. Okay. Then equilibrium mole total number of moles will be 1 plus xi. Total number of moles will be 1 plus xi. Equilibrium mole fraction will be 1 minus xi divided by 1 plus xi. Here 2 xi by 1 plus xi. What is mole fraction? Number of moles by total number of moles. So if I write the equilibrium constant in terms of mole fraction, what is equilibrium constant in terms of mole fraction? mole fraction of the products raised to their stoichiometric coefficients divided by mole fraction of the reactants raised to their corresponding stoichiometric coefficients. That's what I have done here. Mole fraction of the product raised to their stoichiometric coefficient, mole fraction of the reactant raised to their stoichiometric coefficient. If I rearrange, I can say that I can separate two things. The first thing is, this is total number of moles. 1 by 1 plus xi is the total number of moles. This is the common term I have separated. 1 plus xi is the what? Total number of moles I have separated. So I have got a polynomial kind of expression in terms of xi. What is xi? Extent of reaction. I have got a polynomial expression in terms of xi, or the extent of reaction. If I solve this expression, I can find out what will be my equilibrium constant. So this is the first example. Now second example is what? Second example is formation of ammonia. Again, N2 3H2 gives rise to 2NH3. The initial number of moles is, this will be also 1. Again, there is a printing mistake here. Initial number of moles, let the initial number of moles is 1, 1 and 0. So equilibrium amount will be 1 minus xi, 1 minus 3 xi, 2 xi. So the total number of moles will be, if you add all the number of moles, you will get 2 minus 2 xi. So the mole fraction will be 1 minus xi by 2 minus 2 xi, 1 minus 3 xi by 2 minus 2 xi, 2 xi by 2 minus 2 xi. So the equilibrium constant in terms of mole fraction will be mole fraction of the products raised to their stoichiometric coefficient divided by mole fraction of the reactants raised to their stoichiometric coefficient. Again, I can separate the total number of moles. This is just a rearrangement. And the total, what is the total number of moles here? 2 minus 2 xi. Again, this is a printing mistake. This should be 2 minus 2 xi. This will be 2 minus 2 xi. Two mistakes are here. This 0 should be 1 and this 1 should be 2. In both the examples, again, here is the equilibrium constant in terms of mole fraction is again a polynomial in form of xi. So in both the example, and polynomial xi is obtained, the polynomial will always have one positive real root. For quadratic equation, we can solve this polynomial easily. But for higher order polynomials, the solution is obtained by iterative methods or mathematical application. So what is the solution to our objective? What was our objective? Our objective was to study what is the effect of initial composition or initial concentration on equilibrium constant. So we try to obtain an expression, but every time we are getting a polynomial in form of xi or polynomial in form of extent of reaction. To generalize, these are the two examples that I have given. One is decomposition of nitrogen tetroxide, the second one is formation of ammonia. So if we give a generalized equation, we'll get the equilibrium constant in form of mole fraction is given as 1 by N0 plus V xi. This N0 is initial amount of gaseous reactant and mole, and V is stoichiometric coefficient to the power V. Then this is pi product operator Ni0 plus Vi xi I to the power Vi. This is a general to summarize all the examples. This general expression is applicable to all kinds of reactions. So this N0 and V xi is the total number of moles for any reaction. If you take the total number of moles will always be N0 plus V xi. For ammonia it is 2 minus 2 xi. So what is 2 here? N0 was 2 because 1 plus 1 is 2, minus 2 xi plus V xi means here it is how many number of moles. In the product side 2 number of moles, reactant side 4 number of moles. So 2 minus 4 is minus 2. So N0 is 2 minus 2 xi. So 2 minus 2 xi is the number of moles, total number of moles. It will be applicable to all the reactions. Okay, so this is a generalized reaction. Now to our problem. What was our problem? What is the effect of concentration of the reactants on equilibrium constant? To summarize that effect, we can show the exact relation depends upon the solution of polynomial expression, that is on root of the polynomial expression, because we have seen in both the examples every time we get a polynomial in form of xi, Xi is what? Equilibrium, sorry, extent of reaction. So if we solve those polynomials, we can obtain a expression for equilibrium constant. So with this, I'll stop here. Thank you.